Well, now we know how far average of your sample can be from the average of your population, but the problem is this distance is also random, so we never know if it's a small distance or large distance. However, we can compute the boundaries of this distance, and that's what exactly confidence intervals are. So let's learn how to do it. In this case, let's recall first of all that average of your sample. So if you take, for example, 10 glasses of water from a lake, estimate how much of, for example, chloride you have in every glass and compute average chloride content, then this average value that you computed will be a random number distributed around the true population average with this standard deviation, which we call standard error, right? And why I say it random number, it means that if you take another 10 glasses of water from the same lake, you will get another average. So that's why it's called random number. We know that the last part in this sum, this part, which we call error margin, it's exactly something that defines the distance between m and mu, but we also know that this distance is random number because z is random number. On the other hand, we know that z is bounded depending on the percentage of cases or depending on the probability of the outcomes, right? So let's use this knowledge to estimate average of your population not as a single value, but as an interval. So let me give you some example. Let's use an example that I used already before about height of female persons in United States. So you know that we have a population parameters in this case. So we know that the average height of females in United States is 165 centimeters, and the standard deviation is 6.6 centimeters, right? It's exactly this information I got. Now let's use this to answer the following question. If we randomly take 2.5 thousand women from the whole country, so it should be a random representative sample, if we measure height of these women and compute average height of these 2.5 thousand women, how close this value will be to the true population mu. Okay. So how we can compute this? First of all, we need to compute a standard error. So we compute this part. And we know it's easy. You take a standard deviation of your population, divide the square root of the sample size. In this case, sample size is huge, the square root of 50. And then that gives us standard error. So this is like a measure of this distance. Now, we know that in 95% cases, Z score is limited by plus minus 196. So this is something about the normal distribution that we already learned. But what it means that we can use these bounds, we can use these boundaries and compute interval of possible m values that we can get in future, right? So first of all, we compute the error margin. And you can see because interval is plus minus 196, I simply take 196 times 0.13. That's exactly the error margin, right? It's z-score, maximum z-score times standard error. And now we can compute the interval. How? So apparently on one side it will be mu minus 196 standard errors. And then on the right side it will be mu plus 196 standard errors, right? And that's exactly this one. So if you take 165 and subtract 0.25, you will get 165, 4.75. If you take 165 and add this, you will get 165.25. So what it means, this is my expectation from future experiments. So if I indeed make this experiment, I describe it here, the average I get with 95% probability will be bounded by this one, by this range, by this interval. And I can repeat this for any probability. So in this case, I choose 95% probability, right? So 95% cases. I can do the same for 99% cases. In this case, I need to find out z-score for 99% cases. How you can do that? You remember that if you have normal distribution, standardized normal distribution, so you have z-scores here, then if you have 99% inside, so this is the left, this is the right, let me call it z1, z2, then you have 1% outside, but this 1%, it's equally distributed on both sides. So here you have 0.005, right? It's exactly half of percent. And this is also 0.005. So strictly speaking, I shouldn't use percentage here. The area will be 0.99, okay? But you got the idea. Now I can compute Z1, for example, as using the ICDF function. In R, it's a Q norm, right? Q norm. For 0.005 Or I can compute Z2 as a Q-norm. And then I need to take this plus this, because you always have area on the left, right? So it gives me 0.995. And if you run this or this in R, this will give you minus 2.58, and this will give you 2.58. I recommend you to check it, but I will continue meanwhile. So this is my boundaries of Z-score. So I know that if I take 99% of most common cases, Z-score is bounded by these two values, minus and plus 2.58. Now I can compute the error margin. It's simply the Z-score times standard error. So this is my error margin. This is the maximum distance between M and mu. So it's a maximum distance between M and mu. I expect in 99% of the cases for this particular situation, right? And since it's a maximum, I have these boundaries. I can bound the possible outcomes. So simply I take the average of population minus this. So that will be the left or lower boundary. And then I take average of my population plus this value. That will be the upper boundary. So this is the bounds of my future M values. Okay. So it doesn't sound very practical so far, because we simply predict average of our sample that we are going to take in future. But you can say, but it has no sense, because you can compute this average. Yes, but this is just one step towards the real practical value. Okay. Before we talk about the real practical value, I recommend you to play a little bit with Grasta app, which it does exactly the same. It computes these intervals of sample means based on the population parameters. And in the next video, I explain how to use this app. And then when you come back, we will continue talking about the intervals.